So here we're just going to talk very briefly about how to generate filter coefficients using PureData. Now, there are obviously infinitely many reasons why we might want to do this, but to specifically address why we might want to use something other than the blocks that are already provided by PureData, for example, the VCF object is relatively limited. I believe it provides a fixed first order low pass filter, and it does allow you to modulate the cutoff frequency as a function of time, but it does not allow you to modulate the Q of that filter as a function of time. So the Q is fixed. If we can generate our own filter coefficients all as a function of time, then we can have both the cutoff frequency and Q be modulated. So of course, for applications and synthesizers, it's very common to modulate both of these attributes of the filter. You might connect them to an LFO or to an envelope generator. And so doing this can be useful. And again, the VCF object will get you pretty far, but if that leaves something for you to be desired, then this method will work a little bit better, or will give you more options. So this is our guide here. These filter coefficients, or the formulae to generate them, come from an AudioEQ Cookbook text, and it's very common for DSP hobbyists to use this text. You might have come across it. I'll link it in the description. These coefficients specifically are for a low-pass filter. There are slightly different coefficients for different filter shapes, and you can implement them much the same as I'm going to show you how I've implemented these. But you'll see that these 6 coefficients, B0, B1, B2, A0, A1, and A2 are my 6 outlets of this patch here. B0, B1, B2, A0, A1, and A2. And I have 4 inlets: cutoff frequency, Q, and then mod freq and mod depth. So we'll just start with the cutoff frequency. We ultimately want to get to this omega naught term, and omega naught would generally be 2 times pi times fc divided by the sampling frequency. The cosine block, however, automatically takes its inlet and multiplies that by 2 pi and takes that as the argument to the cosine function. So to get to omega naught, really all we have to do is take fc divided by the sampling frequency and pass that directly to the cosine block, because the cosine block will internally multiply by 2 and multiply by pi. So it's at the outlet of fc, essentially, that we want to introduce our modulation. And in fact, we want to do that here. I've made a mistake here. So the modulation frequency, of course, can be anything you want. For an LFO, that might be something at 1 hertz or even lower. And the depth will be how many hertz we are modulating by directly. So if I am adding to FC, then I'm basically just changing FC as a function of time. Now, of course, the outlet of the oscillator block will always be bound by -1 and 1. That's the range of outputs for any of your standard trig functions. They're oscillating between -1 and 1 as a function of time. So I want to multiply that by something to change FC. So if I multiply this by 2000 now, here at the outlet of that multiplication, I'll have something that's oscillating between -2 and +2. And if I am adding that directly to FC, then of course my FC is now changing, and you can see that is in terms of hertz, the depth on the modulation. So like I just realized, I've set this up incorrectly. Now this is where I want to introduce the change in FC. And I need to, it's probably not going to let me connect this here. And that's because this now needs to be a signal input. So now let me drag this up. Now, of course, any of your blocks that are doing operations on signals need to be marked as such. So this addition here, where I'm adding the output of my LFO essentially to FC, is a plus object with a tilde, which means it's meant for signals. And, oh, right. So the reason that I can't add that here is because this also needs a tilde, and how it will work. Fantastic. These number objects don't really work on signals. They'd be displaying values that are changing rapidly. So I want for this to also be a signal. Great. Oops. Okay. So right, if this is set to 0, if the mod depth is set to 0, then I'm effectively adding nothing to the FC, and I'll get a constant output here, 1,000 plus 0 all the time. So I'm just going to get 1,000 divided by 44.1, and that'll be the input to the cosine block, which we've talked about. Now you'll see we have this intermediate thing here called alpha, which uses a sine of omega naught. And there is no sine block, but we can just use a phase shift to essentially yield the output of a sine function from a cosine function. And that phase shift would be a factor of negative pi over 2. But again, because the cosine block multiplies its input by 2 pi all the time, that means we need to roll out 2 pi from pi over 2. So pi over 2 divided by 2 pi is 1/4. And that's why we have the FC being multiplied, FC divided by 44/100 minus 0.25, and then going into the inlet of the cosine block. That'll essentially yield sine of omega naught as opposed to cosine of omega naught. And then we'll divide by 2 and divide by q, which is the same as dividing by the quantity 2 times q. Now q here is not itself a signal. Of course, it could be made to be a signal much the same as we've made FC a signal. So we've made FC a signal by taking a fixed value and adding some LFO to it. You could copy this, paste it over here, and do essentially the same thing. Have your kind of fixed Q, your baseline Q, and then add some LFO to it. And of course, the rest is quite simple. Again, as we've said, even for these basic mathematical operations, these are some additions here. You need to make sure that your signal, or you're using the signal versions of these simple mathematical operations. And the patch wires denote whether what's being transferred between the blocks is a signal or not. So you'll see that this is just a value, it's a float, it's a number. This is a thin line. FC, when it comes in, is just a number. And then what we're dealing with here are all signals. So this is a thick black line. And we'll talk in another video how you actually use these coefficients to create a filter that varies over time. But needless to say, this is how you can take these simple quantities FC, Q, and modulate them, turn FC and Q into signals, and generate your 6 coefficients, all as a function of time. And again, you can use the AudioEQ Cookbook that will be linked to set up a slightly different version of this type of patch to create different filter shapes.